So thank you all for coming for this new reading group session of ContinualAI. This time we have the pleasure to host Luis Herranz, that is going to talk about his recent work on Bookworm Continual Learning, beyond zero-shot learning and continual learning. So thank you, Luis, for being here. And if that's right for you, you can start.
Okay. Thank you, Vincenzo, for the invitation. It's a pleasure to be here sharing this work. So this is a joint work with Kai Wang, Anjan Dutta, and Jos van der Weijer. It's a bit about integrating series of learning and continual learning. So it's and this is we are from the Computer Vision Center in Barcelona. Anjan now is he moved to the University of Exeter in the UK. So just a quick introduction of our center. It's a small center, but very active in computer vision in the Autonomous University of Barcelona. So you're welcome to visit us. So I want to talk about what we call bookworm and generalized continual learning. So I like to think, to find some inspiration, what people would, we try to find inspiration in humans, no? So I like to do this sort of silly cartoons in which I think, like, I picture this little girl reading books, like an album, and you have images and you have the corresponding labels. So this is a learning process. And now the girl sees a new cat, a new image of a cat, or visually a cat, and she knows how to recognize this cat because she has seen the cat before. But if she comes across an animal that she hasn't seen in her books, then she doesn't know the animal, or probably she will predict that this is a horse. Anyway, at some point, someone can tell her, or she can read it in the zoo, like some sort of caption or something, that this is really the name of this animal is zebra. So this is another learning process, no? So this is what we call continual learning. No? She doesn't need to study again the books to know what cat horses are, but as we know, machines have some problem with that, this catastrophic forgetting. So then now she can recognize these zebras, but also can recognize cats and horses, no? If she's not forgetting. So this is the way I see continual learning. And when we want to study this, we tend to divide this into tasks. So I will also do that, but still this is a bit not so arbitrary. It's a bit arbitrary, this division into tasks. So just a quick summary, how can we address continual learning? Typically, we have these three families of methods where you can regularize the weights, the parameters, like EWC, or you can regularize the features with respect to a snapshot of the network before starting to learn the new task. You can regularize the features using distillation, for instance. You can also prevent forgetting, just including some exemplars from previous tasks. That's known as rehearsal. You can also, instead of learning the exemplars, you can just learn a generative model. That would be pseudo rehearsal. You can also isolate, just prevent forgetting by preventing the interference, by just not touching the parameters that have the knowledge of previous tasks. So, okay, in this case, in this paper, we focus on pseudo rehearsal, and in particular, we do it at the feature level. So, this generative feature replay actually. So we have this paper in a continual learning for vision workshop at CVPR that we compare generative image replay. Just you want to generate the pixels, the images, and then include it in the training of the classifier. And we evaluated doing this at the feature level and using distillation. So and we found that doing this at the feature level is more effective, and also it's easier to train the generative models, generators. So we are going to, in this work, we are going to also follow this feature generation, feature distillation framework. Here in this paper, we used a GAN in this. In the paper of this presentation, we use a variational autoencoder, but the idea is the same. Okay. So now let's consider zero-shot learning. So in this case, the information the girl has in the books are descriptions of the animals. Sometimes she may have images of the animals, like here for cats, and she will learn that cats are small, typically furry, they are carnivorous mammals, so on. Zebras are like similar to horses, the same family of horses, as black and white stripes. But in this case, she hasn't seen any zebra yet. So, okay, she's still learning. And she can recognize cats. And also, at the same time she's recognizing cats, she can pay attention to the attributes of the cats, like furry and small. So she can learn also the texture of fur. But not only can recognize cats, she can also recognize zebras if she is able to do the inference from the visual information to the attributes, and from the attributes to the class. So that's the zero-shot recognition. And usually it's divided into scene categories, those that they have visual information available, and unseen categories, those that don't have visual information available, although the descriptions are seen, of course. So what we propose in this paper is, why don't we combine both functionalities? So, and we can consider also that zero-shot is following a sequential structure. So here we can continue recognizing the cat, and now when we come up with a zebra, and we don't know, we know it's a zebra, or we guess it's a zebra from the attributes, then someone tell us it's actually a zebra, or could correct and tell just this is not a zebra, this is a different animal. So in that moment, the girl can update her knowledge about zebras. And then next time she sees a zebra, she could also leverage that visual knowledge. So this is basically the idea. The paper, the first in the what we call here bookworm, what we are assuming is that she doesn't. All the semantic descriptions are known beforehand, okay, prior to this continual learning phase. The metaphor is that this girl likes to read a lot of books, but hasn't explored too much the world. So now, after reading a lot of books, she goes out and explore, or goes to the zoo or whatever, and wants to explore. And we would like to know if all this knowledge that she has acquired can help compared with not having that knowledge. That would be conventional continual learning. So just a quick, for those who are not familiar with zero-shot learning, I have here a couple of slides to introduce how this is usually done. So in this case, we have a classifier trained with 4 categories, but zebra is not in that category. So basically, you cannot know what is. Your vocabulary doesn't include zebra, so you will predict probably horse or something. So the key is to connect the unseen categories with the seen categories. And how can we do that? Well, we need some sort of semantic, leverage some sort of semantic relations. Okay, and these semantic relations, here we call it semantic model. That could be, for instance, attributes that are shared between the seen categories and the unseen categories. Could also be learned from a large corpus of text and map into a word embedding. Similar concepts would be closer in space. So this is an example of typical visual semantic alignment. So instead of connecting directly the categories with the images through the neural network, what we can do here, if we have a semantic model, is to project them to the categories to the semantic space. In this case, could be a word embedding space or an attribute space. And now, in this paper, for instance, in device, it's a classical paper in zero-shot learning, what they propose is learning a mapping. So now we can also map the images to the same space as we map the categories. So the advantage of this is that if we have now another category, we can still map it to this space, but also using the same neural network, we can map the image of an unseen category using the same mapping. Even the CNN hasn't seen any zebra, but can map it to that space, and hopefully it will end up closer to the word zebra, to the location of zebra. So basically, here what we do is a nearest neighbor search to find the most likely category. This is how it's done. This would be the semantic model connecting the visual information and the attributes and the categories through an intermediate layer of attributes in this case. So another approach to perform zero-shot learning is using feature generation. So in this case, we can learn to imagine, let's say. So if we have, if we know what orange means because we see giraffes, for instance, or tigers, and so on, we have seen animals with stripes, so we know the concept of the stripes and so on, and other colors and so on. We can condition a generator, for instance, a gun, on those attributes, and then we can generate images, or in our case is features, of those unseen categories. In this case, leopard and cow. So now we can use that data that we generate. We can use the real data from the seen categories combined with the generated data of the unseen categories. And now we have data for all the categories, seen and unseen. We have visual data. So now we can train a conventional classifier. So now you can see that here the the semantic model is only used for during the generation, which can be seen in this case as a sort of data augmentation for the unseen classes. But there is no intermediate semantic space in this case. So we are going to use this approach in the Bookworm Continual Learning. So we can see that, again, zero-shot learning, it's can be said as continual learning. So first, these are the descriptions we have. So we have, for instance, seen categories like polar bear with the corresponding images, and unseen categories like zebra. Now let's forget about the images for a moment. Let's put them here. And now we also have the corresponding labels of these images. No, so we can learn this semantic model. This could be done in this Bookworm Continual Learning, in this Bookworm phase. So this first phase, we put them at time 0 for convenience. This learning is what we call the Bookworm phase, and learning the visual model is what we call here learning the task 1. Well, the same categories. And then the combination of these two models is our model, continual zero-shot learning model. So we can see that during inference, we have this model. We have part of the model related with seen categories, part related with unseen categories. So in the case of zero-shot learning, the original, the early zero-shot learning was only evaluated on the unseen categories. A more challenging setting is generalized zero-shot learning, where you evaluate on both seen and unseen categories. But here the question is, okay, so if we have seen the zebra, why don't we continue updating the visual model? So that is what we would do in this Bookworm Continual Learning. So now we want to formulate this in a more continual learning fashion. So instead of seen and unseen, we call them task 1 and task 2. And now we observe new data of this task 2, and we want to update the visual model. This is essentially the idea of this. But another question is, why the semantic model still remains fixed? So why don't we can update it also? So that is what we call generalized continual learning. So it would be a generalization of Bookworm Continual Learning also. So just to compare them quickly, this is essentially the same I mentioned before, but look at the bottom. That is, let's say, the functionality you have at test time. So when you have only seen task A at time 1, you cannot predict anything from task B. In zero-shot learning, but at time 2, you can predict both. In zero-shot learning, it's sort of, once you have learned task 1, is finished. I mean, you are not going to update anything. So at time 1, time 2, doesn't matter. You are going to only predict the first task, the seen categories, directly using the visual information, but the others are going to be indirectly using the semantic model, zero-shot prediction. And in Bookworm Continual Learning, you can predict both all the categories at any time, all the categories that you have, say, learn about in the Bookworm phase. And then when you observe new visual information, you can update it and you can hopefully do a better prediction, because now you have actually seen the categories. And this generalized continual learning that I said is essentially as one step further, just assuming that at any point, here I'm also showing this in a stream setting, when you are getting information as you are as time passes, you can get different types of information, visual information with the label. You can get descriptions and with the corresponding images or image. The label, you can get just the description and the label, so that you would update your semantic model. So this is just a setting, but we haven't worked in this setting yet explicitly. And this is a comparison of all these models. So what we call here joint training is the conventional conventional machine learning setting. You need to have everything in advance beforehand. If you don't have it, then you cannot predict anything else outside that data. Continual learning, you can see that we can update our visual model, and we can, but essentially, yeah, we can make predictions on new categories, but only those that we have seen. And then the other four settings are settings including semantic models. So you have zero-shot learning, generalized zero-shot learning, Bookworm Continual learning that somehow extends all the previous ones, generalizes the previous ones, and the generalized continual learning generalizes the Bookworm Continual learning by allowing the semantic model to be continual. So here, that's the setting of the problem that we think is very interesting to move in that direction of including semantic information in continual learning. We address this Bookworm Continual learning setting with a framework we call bidirectional imagination, which is based on essentially on feature generation. No? It's a extension of the feature generation framework. So this is an overview of the approach. We have to solve two problems related with continual learning. We have to alleviate the catastrophic forgetting, and we have to provide zero-shot inference to the model, to the system. So our framework is based on feature generation. Why? Because the same mechanism of feature generation can address these two main challenges as I described before. So you can reply previous tasks to do pseudo rehearsal, or you can imagine future tasks, future categories. So it seems very well suited for our purpose. So we call this bidirectional imagination because if we consider that replay is also some sort of imagination, it's like imagining recalling what you saw before, it's sort of also imagining back. So we call it in that way because we go in both ways. We want to generate past and future categories because we don't have data from either of them. In this case, we use a variational encoder. So you can see here how. So this would be the feature generation. You can see that the images on the left are not very realistic. They are generated with a GAN, actually. So that will be the data we use as replay data. And on the right, you have something similar. Those are the categories you have imagined. So that I already explained this. So now what we do is to combine both. So now we are generating future and past features. Our first approach is a naive approach. We simply use a zero-shot learning framework using a variational autoencoder. And we condition, instead of conditioning on the class, we condition on the attributes. Also the past categories. So we can, we always go from class to attribute, and then from attribute to visual features. So these are the components. So here we have, keep in mind that now instead of having a direct connection from class to the generator, now the generator is conditioned on the attributes. So now what we have is another generator, which is conditioning on the class, and now generates the attributes that is going to be the input to the generator. In this case, the generator is the decoder of the variational autoencoder. So that's why I say here we have a hierarchical generative replay, because we first replay the attributes, and then we replay the features. So these are the components. So we have this feature generation, variational autoencoder. Then we use also feature distillation. And then we also use distillation in the decoder, because we also have to prevent forgetting in the decoder. And we use the replay alignment that we used before in the memory replay GANs paper, and it's very effective preventing forgetting. In generative models, we use it in a GAN. Here is a variational autoencoder, but it's the same principle. Okay, so how do we train this model? So the first stage, we simply we want to prevent forgetting in the. We want to train the feature structure. So to prevent forgetting in the feature structure, we use distillation. And we train a classifier, but this classifier is a proxy classifier. Then we won't use it later. The second step is training the variational autoencoder. So we feed the autoencoder with the images, well, actually see the features and the attribute that is a condition, and we train the autoencoder. And at the same time, we also use the replay alignment trick to prevent forgetting in the decoder. So the idea of the replay alignment is that you have a snapshot, it's the same as distillation, no? So you have a snapshot of your decoder at t-1, and you want to keep it as close as possible. So for the same random vector, because remember that all of this is stochastic, so this is sample from a Gaussian R. You want them to be exactly the same random vector, because then you want that whatever the decoder is replaying, whatever dt-1 is replaying, you want that dt is also replaying, and this is a pixel-wise loss. And this works because dt is a copy of dt-1. If not, it wouldn't work. It's a copy that is being updated, but is significantly aligned. Okay. Now the third step is training the classifier. I didn't say, but the encoder, we train the encoder every time step as a new encoder. If I'm not mistaken, the variational autoencoder is just 1 or 2 layers, the encoder and decoder. So it's very efficient. The final step is, once we have the generator, the decoder, and the feature structure trained, updated, we keep them fixed, and then we update the classifier that is also trained from scratch. And then at inference time, during the evaluation, we don't need the variational autoencoder anymore. So it's just a classifier. So then we have several variants. Vincenzo, let me know if I'm taking too long. I'm just checking the
we
time.
have reached like 30 minutes presentation.
Yeah, I mean, how long?
So if you want, you can continue. I don't know, for another 10 minutes maximum, but it's up to you.
Okay. Well, then I continue. Let's just notice the time. So we also try different variants of this model. So for instance, one particular case is when your model, I didn't mention that the generator, I mentioned this quickly, is simply a mapping from the attribute to the category to the attribute. So it's just the description of the class in terms of attributes. So if that mapping is the identity, then what you are doing is recovering a continual learning model, no? Because now it's not informing you about the attributes. So now what you have is a continual learning feature generator based model. So we call this class BImag because now it's conditioned on the class. And one interesting thing we found is that our model with attributes is performing worse than the model, the continual learning model. So is forgetting more. So this is an important thing because it seems that the semantic model is harming the replay of past tasks. So now we have here some example that might illustrate why. So I mean, ideally it's not very why it should work. Why it's harming, it's not clear. But if you look at the actual data we are dealing with, so these are examples of the class cow. So you have a lot of diversity, as you can see. So the class BImag sees this diversity directly. No? So it's a model in the distribution, so it can model this diversity. The problem is that the attribute BImag doesn't see this diversity. What it sees, the decoder or the variational autoencoder sees always the same class description, which is not, it doesn't correspond to any real cow. So there is this type of, so what you are going to eventually generate is average cows. You are not going to generate the diversity of cows. So when you replay with that, it's probably going to harm your continual learning classifier. So some possible solutions. So maybe we can we lost the direct connection from the class to the autoencoder, so we can include that explicitly. No? So this is what we call as a condition. We call it class attribute BImag. Also, there is an additional problem that the autoencoder is observing both visual and semantic information of past tasks because they are seen, but from for future tasks, is not seeing the images. It's only seeing the attributes. So that is this imbalance is not is harmful because you are using the same generator for both, but some classes have been learned only from attributes, some have been learned from attributes and images. So we tried what we call asymmetric generation. That is basically we have two autoencoders, one for the past categories, one for the future categories. And also another problem is that, as I saw in the slide with the cows, maybe the problem is that we shouldn't use an average description. Maybe we should have another generative model that samples from a class, samples diverse attribute descriptions. So that's another possible solution. So I'm going to go over these variants quickly. So here you can see that essentially what we do is concatenate the class vector with the attribute vector. So there is this additional arrow in the middle. The asymmetric variant, you can see that now we have two separated autoencoders, or decoders, generators in this case. One is for the past classes, one is for the future classes. Okay, this comment is wrong. About the stochastic semantic model, as I said, if we could, instead of always sampling this 40% black, 60% white, etc., we can have some stochastic model that could sample maybe sometimes black and white with patches cow, sometimes white, brown with patches, etc., but randomly, and then that instant of cow description is the actual condition to the feature generator. Then that should, in principle, transfer the diversity instead of this bottleneck of this deterministic average description. Okay, so yeah, a problem is that whether it makes sense to have, because to train this you need instance descriptions to train a generative model for the attributes. So yeah, that's a practical problem, that whether it makes sense or there is some scenario where this makes sense. But anyway, so this is an example of BImag with this stochastic model. So you can see here that there is this new variable S that is also sample. So essentially G is no longer a matrix. Now is you could think of another generative model. Okay. Then quickly about the experiments. So we evaluated on 3 data sets, animal with attributes, cube, sun, with 2 splits and 3 task splits. It's also a bit tricky to define the splits. We've tried to follow the zero-shot learning splits. And then we further split them, but we are following the standards in zero-shot learning because we also want to evaluate in zero-shot learning. Evaluation metrics, we are using the area under the sin and sin curve, which is an alternative metric to harmonic mean, which was observed to be very sensitive to calibration. So this is the formula. We also use the overall accuracy. So outlook is say taken from generalized zero-shot learning. We adapted, instead of calling sin and sin, we call it task accuracy. So instead of sin accuracy and sin accuracy, we call it task accuracies, to be more general. But anyway, and we evaluate in Bookworm continual learning setting, but Bookworm for time equal 1 means that you haven't updated your model. It's also generalized zero-shot learning. So that's what we evaluate. So these are some examples on some experiments for generalized zero-shot learning. So we found that actually this joint conditioning, including the class in the conditioning, it's also improves generalized zero-shot learning. You can see here the metric. Then going to 2 tasks, you can see here that the one that performs best in 2 tasks in cube and animal with attributes is this class attribute conditioning. And both you improve over the continual learning and the attribute conditionally. For 3 tasks, the asymmetric variant seems to perform best. So you see that sometimes one of these tricks works better than the others. So finally, the conclusions. So what we wanted to do in this work is to study the role of semantic models that we think should be considered as an integral part of continual learning, because humans, we think in terms of not only visual information but also semantic information. So we think that the machine should also somewhat integrate these two components. We propose two new settings that we call that integrate semantic information together with visual information that leverage semantic information. Generalized continual learning and Bookworm continual learning. So Bookworm continual learning generalizes both continual learning and zero-shot learning. The semantic model remains fixed, and the generalized continual learning allows this semantic model to be updated continually. And okay, so well, there are many questions, many open questions. This is still ongoing work. There are very tricky things like defining the settings, the splits, what data sets, how do you evaluate this, use zero-shot style evaluation metrics or continual metrics, continual learning metrics. Honestly, it's not very clear to me, some of these questions. And conclusions about this bidirectional imagination framework, which is just a particular implementation of Bookworm continual learning using feature generation, generating in both directions, the past and the future. An important finding is that integrating this semantic information is not trivial and might interfere with this feature generation. We propose some possible solutions like joint class attribute conditioning, decoupling the directions with asymmetric generation, and perhaps using stochastic semantic models instead of deterministic semantic models. But anyway, there is still a lot of space for improvement. Some mention of other works in continual learning and zero-shot learning in our group. Yeah, and then this one in generalized Bookworm continual learning. And yeah, these are the co-authors of this work. You can find more information in my web. The paper is in archive. Was also a short version is also in the task CV workshop in ECCV. Yeah, and I also have a blog. I have some posts about continual learning. If you are interested, I leave there the address. And thank you very much.
Thank you, Luis, for your great talk. It was very interesting. I think especially in the idea of trying to put together these two different, let's say, differently fields like continual learning and feature learning that has been like treated like separately in the last few years. I think maybe I can start with a question just to break the ice. In this work, you try to use this semantic model as being used in the past also for feature learning. But do you think it would be useful as well in continual learning, where you have a lot of data for each task, or is just something that it's useful when you have just few data for each task, like in the zero-shot learning case and scenarios?
Well, I think the thing is that you never have enough data for all the possible classes. So sometimes you can have some descriptions. So I mean, of course, I think if you have enough data in a pure continual learning, I don't think that semantic information can help. I mean, you are probably saturating the performance if you are able to prevent forgetting and so on properly. I mean, probably then semantic information might be not helpful and probably will be might be harmful if you are trying to feed the semantic information, as we saw in the as I explained before.
Yeah.
Maybe that is what is you are trying to feed the semantic information that is not is very noisy, very imperfect. For instance, this example with the cows. So it's probably better just to, as I saw, to just give all the visual information of the cows. The autoencoder is going to learn the diversity. While if you try to impose some semantic structure that is not very rich and not very could be noisy and so on, could be you're maybe shooting your own foot. You know what I mean?
Yeah.
So it's a tricky thing, but in general, I think there are sources of semantic information, text, and so on, that we could leverage. So I think for a more, let's say, advanced continual learning, I think could be an interesting direction. Also, I want to also mention that there is another paper, AGEM, that also have some section in the paper using using some attributes. In that case, they frame it not from our perspective, but it's more like from the perspective of accelerating the learning. So the thing is that if you haven't observed enough data because you are at the beginning of your learning, you can do zero-shot inference, right? So at that point, you are going to have better accuracy than with the very few samples you have observed. But as you are observing more and progressing in your learning, then the difference is going to be marginal, and probably there is some point in which you probably should start ignoring your semantic information. I don't know if this answers your question.
Yeah, it does. Thank you so much. So the idea of somehow inferring this semantic model from the data is not that useful. I mean, it's useful when you have this semantic model that is like somehow detached from the data you're encountering, and it's something that adds to the knowledge somehow, and maybe you can have it before starting the whole training phase.
Yeah, I mean, if you have some information that can help, like some semantic information can help, yeah, I think why not use it?
Yeah.
For me, it's not very clear. I'm not sure if I understood properly. You mentioned that learning the semantic information from the data.
Yeah. So the idea that you maybe, I mean, maybe it would be nice to explore the possibility of building this semantic model over time while you learn, and then use it in an interesting way. But as you mentioned before, if you have the data, maybe, I mean, and all the knowledge you already learned from these data in your visual model, then I don't know if this can help in the end for the future learning.
Yeah, well, the question of learning updating your semantic model that's why we call generalized continual learning, because in that case you would be, so that's something we are looking into, but you do have to update, like maybe related with language, natural language processing, and so on. Because one possible semantic model could be word embeddings.
Yeah.
So we've been looking into that. It's not easy. But learning the semantic model, in principle, you have to have like a explicit semantic. I mean, my point is that it's very difficult to learn these attributes, for instance, from images only. You need to have some source of semantic annotated information with the attributes on something like that, or external source like Wikipedia to learn your word embeddings.
Yes.
So I tend to see it more like, maybe if you are thinking only in terms of classification, it's difficult to get beyond this zero-shot classification. But I think that if we are going to aim at more complex tasks that also involve, for instance, text, or then it needs to be considered as an integral part of the continual learning system, I think.
Yeah, that's very interesting too, as a way of integrating multi modality into your continual learning system. That's also very interesting. So do we have any more question for Luis?
Hi, can I have a question?
Sure, Joseph, go ahead.
Yeah, so in this specific model, while we are trying to learn a new task, let's say T+1, do we assume that we have access to the attributes of, kind of like all the future classes that are, or rather tasks that can potentially be seen to by the model? So to put it very straight, so do we need access to the entire attribute of all the tasks while we are training on, let's say, a task 0?
Your question is, do we need to have information for all the categories, all the descriptions of all the categories from the beginning?
Yes, that's true. Yeah. So in a zero shot or a few shot setting, that is implicit. I know, like we know what are kind of labels to expect, and then we do have all the attribute, let's say attribute class or attribute vectors for all the classes that can probably be introduced to this model. But like in a continual learning setting, I believe that cannot be assumed because we just cannot know. We just don't know what to expect in the future. So I just wanted to know, like, whether in your formulation, are you expecting that we will have access to the entire attribute space while just learning task 0? Or
That's actually, that would be the difference between this bookworm and this generalized. Because in the bookworm, you're assuming that all the semantic knowledge you studied, the time 0. And that includes
Sure.
that includes that you cannot have more categories, for instance, or you cannot have more attributes. So that would be part of this generalized continual learning setting. If you have that ability of extending your categories, the thing is that that's the setting of in zero-shot learning. There is also some subtle differences on what you are assuming. That sometimes I think sometimes the comparisons in zero-shot learning are not completely fair because some methods are assuming that you know the future, the unseen descriptions. So for instance, let me go back to one. I don't know, can you see my slides still? So just as an example of that, in zero-shot learning, so in this case, this is zero-shot learning using feature generation, right? So here, in the end, you are going to have a data set with all the seen and unseen classes. So here, you have to assume that you know all the classes, including the unseen, right? But if you use this previous method of visual semantic alignment, the only thing you have during training is this. Okay, you don't have the zebra here. Okay, so now let's say we are in a continual setting, and now you come up with the description of zebra. You can map this zebra to this space, and you can use the same model to map it. So in this sense, visual semantic alignment is continual.
Yeah, the
Does it make sense?
Number of attributes are fixed, though.
The number of attributes are fixed, but yeah, I mean, this is actually something I was considering. And so it's true that this feature generation approach assumes that you know all the unseen categories. So that's why sometimes I think it's not so fair, the comparisons of this generation models with, for instance, this family of models, because there is this subtle assumption that you know the future.
Yeah.
But anyway, this is just a random comment on that.
Yeah, thank you, Lewis.
Yeah, okay.
That was very interesting. Maybe I have another question. If isn't there anyone else willing to speak? So I'm a fan of generative replay in the latent space. So I was wondering, since I think you proposed yourself introduced the memory replay alignment, right, technique in the past.
The replay, the memory replay guns, yeah.
Yeah. So so in that case, the replay alignment was on the input space, on the images themselves, right? So in this case, instead, is in the feature space. Did you find any particular difference? I mean, in some cases it works better. Maybe I mean, on the pixel space it works better, or in the feature space.
In this work we didn't
an important impact, or not.
In this work we didn't consider the pixel space.
Yeah, right. No, it was a more general question on replay alignment, if it works better in the feature space or in the input space.
So yeah, I have this slide because there is this other work that was also presented in the reading group by Xiale Liu.
Yes.
Which we analyzed that problem precisely. Like if you do this, no, you're asking me about this replay alignment, no? But this
yes.
I think isn't it the same?
Oh, just wondering. I mean,
yeah, no. Here we have image.
When it's. I mean, yeah. Theoretically, I guess it's kind of the same. But when you are in a more higher space dimension, like with the images, I would guess that it's a bit harder to make it work. And maybe you noticed from the experiments that imposing it at the feature level, it works better, but just as a feeling. I mean.
Well, my feeling is that training, for instance, a gun, image level at the pixel level is very difficult, although not efficient. So it's and everything is getting more complicated. So the more parameters you have, the larger the dimensionality, the alignment is going to be more unlikely.
Yeah.
Well, we found that for image generation works pretty well in this memory replay GANs paper. But when then we tried with using that for classification, and we didn't make it work, honestly, because it was just too challenging. And this table here from this other paper shows that for you it's very easy to forget eventually. Yeah. And then if you only replay and align in the block, in the fourth block, then, but yeah, now here I'm a bit maybe I'm mistaking the because the replay alignment is applied for generation, no?
Yes.
Yeah. Maybe I'm just go off a bit of. Then this generation is applied to prevent forgetting. Yeah. So yeah, what they are studying here. Yeah, that's actually a good question. I'm not sure if they studied because here there are two different things. There is the distillation on the feature structure, distillation on the generator. I'm not sure what is the contribution of this distillation in the replay alignment to the accuracy of the classifier. I'm not sure, but in general, I think it's very difficult it's probably a question of complexity in practice. And if you don't have enough data, you probably just go for features because it's less risky.
Okay, thank you so much, Luis, for your time. And I guess I'll see you all guys for the next reading reception next week, Friday.
Okay, thank you very much.
Thank you so much. Bye. See you all.
Bye.